welcome. My name is Bill Venners. I'm going to start 30 seconds early to give you 30 seconds more to ask questions. I looked it up just this morning. I've been working on ScalaTest for over 9 years. The first release, which was called 0.9.0, so it sounded like it was already almost 1.0, was January 12th, 2008. So next January, it'll be 10-year anniversary. And it's used by a lot of people, and what this talk is about is things I've learned over the years. As of, this is June, March, there was the first month where we had 1 million downloads in 1 month. So I was able to tell my wife that she had married a million download heir, and she didn't seem too impressed by that. But that's essentially a big burden on evolving the library because there's so much code out there, you can't just do what you want, right? So what I wanted to do in this talk was talk about an insight that I had recently that took many years to sort of achieve, and then some changes we're planning for the library that fit in with that insight. So it all goes back to this guy. Does anybody know who this is? Does anybody recognize this face? He's a computer scientist who's probably not famous for his face, but for his name is Tony Hoare. So Tony Hoare wrote a paper in 1969, among the other things he did, called An Axiomatic Basis for Computer Programming. And I think a lot of what actually we do goes back to this. Some of the things first came into our discourse in computer science from this paper, and I wanted to point out a few things. And the reason is I kind of want to go back historically to sort of talk about how we got to doing testing the way we're doing it, and to sort of show how I got to where I ended up with my insight. So what this paper, the purpose of this paper, he said, is to provide a logical basis for proofs of properties of a program. And one of the most important properties of a program is whether or not it carries out its intended function. So really, he was trying to get at a way to prove that programs are correct, essentially, that they do implement their intended function correctly with proof. And he said the intended function of a program, or part of a program, can be specified by making general assertions about the values which the relevant variables will take after execution of the program. So there's a couple words there that show up, called, one of them is specify. Another is assertion. So when he says assertion, there was no thing called an assertion in those days that threw something called an exception. So this is really the English or human language sense of assertion. And he says these assertions will not usually ascribe particular values to each variable, so you're not asserting that, at the end of my execution, x will be 12. What they do rather is specify certain general properties about the values and relationships between the variables holding those properties. So you might say, at the end of executing my program or my function, which is a part of a program, x is positive. Or maybe if there's an x and a y, then y will be twice x or something like that. You can say things like that are more general, and then saying exactly x will be this and y will be that. And what he said then was he, in this paper, will use the normal notations of mathematical logic to express the assertion. So what he was talking about the English language sense of assertion, but then what he did is formalize how to express an assertion, which is using logic. Okay, so that was the first piece. The second piece is he said that it's not just at the end of this bit of code that you would make an assertion about variables, but also at the beginning. He said in many cases, the validity of the results of a program or part of a program will depend on the values taken by the variables before the program is initiated. And he called these preconditions, so that's where that word came from. These initial preconditions of successful use can be specified by the same type of general assertion as is used to describe the results obtained on termination. So a whole bunch of words that show up in ScalaTest today show up in this paper, right? Like describe and specify and assertion. So what he said is then, essentially, to state the required connection between precondition P, program Q, and a description of the result of its execution, which he called R, he has this new notation, PQR. See that little thing there is his notation, and that's called a Hoare triple. And what the P is the precondition assertion, which he uses logic to describe, and the R is what he calls the description of the result of execution, which is also an assertion expressed in logic. And then Q is the action that the program takes. So he says the way you can interpret this is if the assertion P is true before the initiation of a program Q, or some piece of a program, like a function, then the assertion R will be true on its completion. And if there are no preconditions, then you just say true QR, because true will always be true. So that always will be met. So no matter what the situation of the planet is when you start, you can actually execute Q and you should see R. So anyway, that was what his paper was about. And what he was really after was proofs, which turned out to be quite difficult to do. So if you fast forward 20 years, or maybe 30, I don't know, quite a few years later, there's this guy shows up and writes a book and a programming language. Does anybody know who this is? Recognize that face? That guy actually is the guy that taught me object-oriented programming when I was a youngster. I was at a company where they were using C, and they had decided to use C++, which was object-oriented, and no one knew what that meant. So they hired this guy to come in and give a workshop, and it was this guy. That is Bertrand Meyer, who designed the Eiffel programming language, and he wrote this book. I took a C++ workshop by this guy, and C++ sort of beat Eiffel in the marketplace. So his workshop was, he would show examples in Eiffel, and then he'd talk about how C++ is like not as good, but because it was a C++ workshop. And so one of the things that he did, and he talks about in his book, that did not get into C++, was this. He goes back to that paper from Tony Hoare, and he talks about PAQ, but he actually changed the name of Q. Q is now what he called a postcondition. He named that. Precondition is what he called P, and then A is the action you take in the middle, like calling a function or executing a program. And he moved the curly braces too, so I don't know why all that changed, but in many, couple decades later, it looked like that. So the idea was, and this is if x is greater than 9, greater than or equal to 9, and that's your precondition, if you add 5 to x as your action, then you can have a postcondition x is greater than or equal to 14. It's also greater than or equal to 15. So, no, it may not be. X is greater than or equal to 14, or it's greater than or equal to 13. But anyway, this is, an example of this PAQ idea. And P and Q are called assertions, and what he did in Eiffel is said, well, I'm not going to try to prove anything. What I'm going to do is just test it. And the way I'm going to test it is put these preconditions and postconditions around the body of a function. So what he has in Eiffel is when you create a method or a function, you don't just say what the function does. You have to specify a precondition clause and a postcondition clause. And what he says is that that's a specification of correctness. So it's the same thing Tony Hoare said, but what Tony Hoare was really trying to get at was setting up a way to prove that code is correct. And what really Bertrand Meyer was sort of saying is, well, let's forget about proof. Let's just test it for a few examples, right? So this is a snapshot of what Eiffel looks like. And what the do block in the middle there, that's where you do something. That's sort of the body of your method. But you can't just say do. You have to say require, and then that's where you put your preconditions. So this is a square root method. So its precondition is that the real number x is greater than or equal to 0, right? Because you can't actually compute square root on a negative number. And then there's an ensure clause afterwards where he's put a postcondition. And so what, in the ideal world, the postcondition for square root would be is that you take the result, and you can just say result in Eiffel, and it means what is going to be returned if this postcondition succeeds. Square it, you should get back the original, right? I mean, if result is the square root of x, when I square result, I should get x. But because it's a real number, in the real world, you may have a little bit of rounding error difference, right? So what the postcondition here is you subtract x from the square of the result, which should be 0 in an ideal world. So then you just take the absolute value of that to make it positive. It should be a positive tiny number. And then you just see that that's less than or equal to a tolerance, and that's your postcondition. So Eiffel made you actually, every time you write a method, think about preconditions and postconditions and sort of specify your do clause right next to it. And so that's what he did in Eiffel. And you can actually do that in Scala. Most people don't know this, but there's an assume and an ensuring method that you can use anywhere in your code. It's from predef, and I'll give you a quick demo. This is just Scala's assert. If I say val x equals 1, and I say assert x is greater than 0, that's going to succeed. I just get the unit value back. If I say assert x is less than 0, this is the assert in predef that's just sort of there by default in Scala. It throws assertion error, right? So what you can say instead is assume, and you get the same behavior. They mean exactly the same thing. It's just assume was intended for precondition checks, and assert was more general. You could use it anywhere. So kind of at the beginning of the method here, at square root, I'm saying I'm assuming x is greater than or equal to 0, and I'm assuming it's non-infinite. And so that's assume. And then there's one called ensuring, which you can call on anything. So I'm going to call it on 42, which is my favorite number. So dot ensuring, that's added with an implicit conversion to any type. And then what ensuring takes is an assertion function. It's going to be passed the value you called ensuring on. So this is going to pass 42 into the function. And then I can say, I greater than 0, which is true. So when that assertion succeeds, it actually returns 42. It returns what you called ensuring on. If it fails, then it throws assertion error. And one of the ideas that Eiffel had was that you could turn these off if you want. So what he was doing is he's mixing test code, sort of, in the production code. So his idea was that you would have these assertions enabled during development and during SQA, but you would turn them off at runtime because they can be slow, or turn some of them off. And he has very fine-grained ways of turning these things on and off. You can turn them off by class. You can turn off just postconditions and leave on preconditions, and that's the default. So the default in Eiffel was that you leave the preconditions in there, but you turn off the postconditions. That was the default. And that turns out to be what people did in the marketplace of ideas. We tend to not do this, and by the way, the example of ensuring here, I do my body, which is math.square root x. And so math.square root already computes the square root, but if you pass in a negative number, you get not a number, right? So what this method does different is if you pass in a negative number, it throws assertion error. So anyway, I call the math.square root, and then I say ensuring, and now whatever that was computed is going to be passed into this function. It calculates the tolerance, which is ULP method, like if the double number is this long in decimal points, there will be a 1 out here. That's unit in the last place. That's my tolerance check. And then you just square the result, subtract x. That should be 0 or close to 0. You take the absolute value and then compare it with tolerance. Right? That's the Bertrand-Meyer-Eiffel way of doing design by contract testing. Essentially, you put it in your production code. And in Scala, you can turn these off. Assume can be turned off. Ensuring can be turned off. It can be elided in your production code if you want. But not many people do that. What we do instead is this, and this is from the Java community. What they did was they didn't do design by contract either. So C++ didn't do it, and Java didn't do it. What Java did is they checked preconditions, but there was no way to turn them off. And we didn't throw assertion error. We would throw things like illegal argument exception or illegal state exception or string index out of bounds exception, some subtype of one of those, and never turn it off. So that's where require came actually into Scala when we were writing the chapter in the book about all this stuff, about assertions and tests. And what was in Scala at the time was assume, which was sort of the Eiffel way, and what we thought made sense to put into Scala was something that was the Java way, which is require. That's where require came from. And then we just don't check the postcondition. Anything goes, right? Except we check it in tests. So we have this thing off to the side that checks the postcondition. So this one, and it's using some kind of example. So it should compute the square root is like a specification of the expected behavior in human language. And then we just try various examples. So here I'm just computing the square root of 42, and that does pass the precondition check, which is in the method, in the require. And then I do the tolerance, and I do that postcondition check. So that's what actually won. That's what everybody does. Very few people do the design by contract thing, or even know those methods are there in Scala. So what I think happened is that design by contract lost to test-driven development. Java really had this huge uptake, and it didn't have design by contract in it. And Kent Beck and Eric Gama made JUnit and went around to conferences and really promoted it and promoted the idea of test-driven development. They made books, and so that's actually kind of what won in the marketplace of ideas. So instead of this, and now this is going back to Bertrand Meyer's take on Tony Hoare's idea of PAQ. And what Bertrand Meyer did differently was he said, well, let's not try to prove anything, let's just test it. But he still was going after that, in the method body, you can see the method body is just a PA and a Q. The P is the assume, the A is the math.square root, and then the ensuring is the Q part, right? So what we do is we do PA true, which we do actually have the preconditions. We put those require clauses in there. And then we, of course, have the A. That's our body of our method. And then we just let anything go. We don't do any postcondition check here. And then what we do is over in this other place called the tests, we check the postconditions on some examples. So what I did in this case is I said for all. So this one says for all x colon x doubles x, whenever x is greater than or equal to 0 and is non-positive, when it's not positive infinity, then and that's the precondition, right? That's the P. Then I have the A right there, square root of x, and then I have the Q, which is the postcondition check. So that's what we do. So what the for all does is it actually makes it a spec. And I'm going to show you what, I'm going to go back up to Eiffel here a sec. Boom. So when you just say PAQ here, no matter what x is passed in, if x is greater than or equal to 0, then the ensure clause should be true, right? So it's for any x that's passed in that's a double. So that when you move it, if it's inside the method like this, then PAQ makes sense, right? But inside a test, to actually make that a specification of behavior, you need to say for all doubles x. If I just say for 42, what I've specified here is that when x is 42, this should be true, which isn't really specifying the full behavior of the square root method, right? So you need a for all to get a specification of correctness once you're doing this other way, which is not designed by contract, but writing tests off the outside. Okay, so what the thing is that for all sounded to me a little bit like predicate logic also. So I wanted to talk a little bit about logic. So this is just a mathematical way to prove things, and it has a very few moving parts here, and you're familiar with most of them. The thing that looks like an A without the line through it is the conjunction. That means and. If you turn it upside down, that's disjunction. That means or. And then the sideways L is a not. So right there, that bit is Boolean logic. So Boolean logic is a subset of predicate logic. And then in predicate logic, you can also have variables, so x, y, z. And you can have something called a predicate. So this one, p, p, q, whatever you want to call them, that is like a function that takes some variables and returns either true or false. So in Scala, we call functions that do that predicates. Like filter takes a predicate, right? It's a function that takes x, y, whatever, and returns true or false. And then there's also just plain old functions like f and g, h, whatever you want to call them, that take variables and return a value. So that's just like a regular function in Scala. So you can say that in predicate logic. And then there's two quantifiers. The universal quantifier means for all. So it's an upside down A. And the existential quantifier means there exists, right? Which is a backwards E. So the mathematicians love to do, like, turn letters around and whatnot. So if you say, like this one right here, the second from the bottom, for all x and y, the predicate P will be true for x and y. That's a statement you can make in predicate logic. And then the second one is, for all x, there exists a y such that the predicate P holds for x and y. Okay, so you can make statements like that, and then the reason you do that usually is so that you can prove things. So you relate like some English statements to a formula in predicate logic, and then you do some mathematical transformations and you prove another statement that you can then say in English. So that's everything of predicate logic. There are two other symbols you often see that you can derive from these. One is called conditional, which is a right arrow, or implication is the other way to say that, and that's really if-then. So if f is true, then g is true. And then if you have the arrow going in both directions, that's the biconditional, or it means equivalence. That's if and only if. So if f is true, then g is true. If g is true, then f is true. Otherwise, they're both false, right? They have to be the same as each other. And that's everything. Going back to this, I noticed was that for all, I mean, it starts to smell like a statement of logic. Like this is a test, and it has a for all on the outside. So it kind of looks like this one down here where there's a for all on the outside. But what's on the inside isn't logic if it's PAQ, because like this, whenever is one statement of predicate logic. Then when I call square root, it's the A, which isn't predicate logic, and then the Q part is another statement of predicate logic. So what the insight I had was that if you go back to Tony Hoare's paper from 1969, he has this little bit in it. When he introduces this notation, he says this may be interpreted if the assertion P is true before the initiation of a program Q, then the assertion R will be true on its completion. So that says if-then. Right? And basically, the way you can read a triple is if-then, which is implication. So that is predicate logic. So what basically I realized is once you sort of, like design by contrast had PAQ in it, which was a way to specify behavior but then not prove but test. When you move things off to the side, it was kind of a hybrid of predicate logic, unless you think of that if-then as part of it. And then you can have each test be represented or thought of as one statement of logic. So it's like for all x, px implies qx. That's sort of a single logical statement that would represent that one test. So it's kind of like a formalizing what a specification means. So in the case of the square root function, I might say x is an element of the double set, the set of all possible doubles. Px, when you sort of, what that means in English is that x is positive and non-infinite. And then qx, here's the trick. What you have to do to get like one statement of logic out of this is take the A and make it part of the Q, essentially. So my Q actually mentions calling square root of x. So I say Q means whenever I call the square root of x, when you square it, that's going to be equal to the original value passed into square root plus or minus a tolerance. So, so anyway, I think that's what a test is. And what it kind of does is we call a lot of things spec in ScalaTest, like fun spec or flat spec. And when you write the name of the test, you might say it should compute the square root. That's a specification, but at the level of human language. Then in the body, if you use a for all, then what you get is actually a specification in logic. So, so that's it. So then what Bertrand Meyer said in his book when he was talking about how he implemented this stuff in Eiffel is that the assertion language in Eiffel is only part of the power of the full predicate calculus. And I showed you all the full predicate calculus. There's not that many pieces to it, right? So what he has, for example, is and. So there's a conjunction in predicate logic. And you actually get that when you're using these assertions that kind of came in at this time where they throw an exception, right? Because since we're not trying to prove anything, what we're really doing is looking for bugs. We're kind of doing science. We're trying it. And if we find a place where the specification is not met, that is finding a bug. And the program can't really proceed when you find a bug because until programs can rewrite themselves and fix their own bugs, some human has to come in later and fix that bug, right? So the best thing you can do is just get out, whether you're actually running in production or like executing a test, get out and give people a nice stack trace that shows them how they got there. And maybe it has an error message that gives a hint at what went wrong. So when I say d.count should be greater than 0, and then in the next line I say d.value should not be empty, there's an implied semicolon between those two, and that semicolon is like and. It's like a conjunction, because both of these have to be true for that to pass. And if the first one is false, it actually throws an exception there and never executes the second one, which is like a Boolean expression that short circuits, right? It does the first one. If that's already false, it doesn't even execute the second one, right? So if the first one is true, then it's going to try the second one, and if that's false, then the whole thing is false. The whole thing is an error. Otherwise, it's okay. So that's you get and, but you don't get or. And in Eiffel, you don't have for all or exists, right? Those pieces are not there. So one of the things that had been noticed in ScalaTest and that people have requested over time occasionally is a way to or matchers. So if this person was saying it would be really nice if you could say d.count should be greater than 0 or d.value should not be empty, right? So you can't say that currently in ScalaTest. And you could implement that in Scala. You could make something like an or that catches the exception on the left and retries it on the right. But I just thought that was exception abuse. I really thought that was going too far. So I never did that. I closed that one, said sorry, no. But it is, I mean, he has a point. It is useful to say that sometimes, right? I mean, what he's saying is very valid. This should be true or that should be true, and I don't care which one. And you can't say that in matchers. So what I did do kind of over many years was add something called expectations or fact, which is a kind of assertion that returns a result rather than throwing an exception. And what the name of the type is fact, so it's kind of like Boolean plus plus. And then there's a type alias from expectation to fact. So expectation and fact mean the same thing. So when you say assert in ScalaTest, that has type assertion. And if it succeeds, it returns succeeded. If it fails, it throws test failed exception. So let me show that. So this is a version of ScalaTest that's in a branch that is like, will probably be 4.0, I think. So if I say assert, well, I need to make an x, val x equals 1. Assert x is greater than 0. So this is ScalaTest assert, so you don't get the unit value back, you get a succeeded singleton back. And that has type assertion, and that's a type alias. The assertion is, actually that's not a type alias, that's a trait, but anyway, they mean the same thing. The only kind of assertion you can have is succeeded. It's sealed. If I say something that doesn't work out, I get a test failed exception, not assertion error. And I get an error message. So the macro will look in there and say 1 was not less than 0. So that has the same features as assertions in Eiffel. They're the same thing. They throw an exception. So you get and, but you don't get or. So if you say expect, that doesn't mean anything in ScalaTest unless you import it. So I long ago deprecated expect. There used to be an expect in ScalaTest because I thought, these should look different. If one of them returns a result and one of them throws an exception, they shouldn't be a mode of assert. It should, assert should always throw an exception, and then this other thing would always return a result. So what it does return is basically a fact is either a yes or a no it's like a Boolean with an error message in it that remembers a fact that was observed about the universe. So it's either a yes or a no. So in this case, I got a yes back because it turns out my expectation was that x is greater than equal to was greater than 0, and yes, 1 was greater than 0. If I do a negative one, I don't get an assertion, I get a no. So it's either a yes or a no. So it's like true or false, right? But with an error message. So this one says, well, the fact, which I observed, was that 1 was not less than 0. The yes and no means whether it was what I expected or not. And then the fact is actually a statement of fact. So I can basically negate the yes and no means whether or not my expectation was met. The English statement says what we observed. Okay, so that's expectations. So what it does is it just implements full predicate logic. So the first 5 combinators are just like Boolean. They work exactly the same way because Boolean's a subset. Boolean logic is a subset of predicate logic. Double ampersand is conjunction that short circuits. Single ampersand is conjunction that doesn't, which is just like Boolean. Most people don't know that's there. In Boolean, it's there in Java. When I came to Scala and I saw this, I was like, why did Scala add that? And it turns out it was in Java. I didn't even know about it. So that's in there. And then double pipe is the disjunction that short circuits, and single pipe is the disjunction that doesn't. And then not is the sideways L, right? That means not. And then there's 4 other things. There's implies and is equivalent to. So that's the one that is, you can actually make these out of these other ones, but it's still kind of nice to have them because people usually have them in predicate logic formulas. So implies is if then, and is equivalent to is if and only if, right? That's the arrow with two arrowheads. And then there's for all and exists, not in fact, but in other places in ScalaTest already. So there's generator-driven property checks, which has for all that takes a generator. There's inspectors that you look at collections, and you can say for all elements of the collection. And then there's table-driven property checks, where you have a for all the rows of the table. And then we added exists also just for completeness to tables and inspectors, but not generators, because it doesn't make sense to have them on generators. But essentially, you have the full power of predicate logic using this. And there is also a form of matchers that does this. So if you use must or should, that is what it does, what it normally does. It returns the succeeded singleton or throws an exception. If you use will, that one looks different. That one will always return a yes or a no. So I can show you that real quick. So I can say x should be less than 0 gives me the, well, that one is actually the exception. I meant to do that. So the one that succeeds, you get the succeeded singleton just like assert. Otherwise, you get test failed exception with an error message. But if you say will, here I'm going to get a yes. Oops, I'm not going to get anything because I didn't import it. Okay, I get a yes with an error message. And if it's false, I get a no. Okay, so that's will matchers. And then what I think it solves a few problems. I mean, for many years, I kind of had this brewing, but I hadn't decided to add it because I try not to add anything unless there's a real strong justification for it. So one of the problems it solves is ORing matcher expressions together. And another one is this thing of labels with, it's kind of nice to be able to build expressions, assertion expressions that compose, and as soon as you throw an exception, you're not really composable. So in ScalaCheck, which is modeled after QuickCheck and Haskell, he uses Boolean to define his properties because Boolean composes. The trouble is if you get a kind of a big Boolean expression and it fails, there's no hint as to what part of the expression caused the failure. So what Ricard put in ScalaCheck is something they had in QuickCheck, which is a label. You can label parts of the Boolean expression. So I can say, well, this first part, if that is the part that causes this expression to fail, after you AND it with the next one, if that's already false, then there will be an error message, result greater than number 1, right? He's just kind of labeling the pieces, and which part causes the thing to fail will show up in the output. And I always felt that was very cluttery. Like by putting those in there, it's hard to see the Boolean expression. So if you're using a fact, you'll get a nice error message without having labels. So that's one of the things I think it allows. It sort of gives you a composable assertion language, but without having to do labels, because you get the error message for free. And another problem that ScalaTest has had forever is that the error messages were nice, but they weren't really scalable when you made bigger assertions. And most of the time you don't, but if I just say assert that x is greater than 0 and x does not equal 1, that's actually not too bad. I mean, this one is, if I say assert x is less than 0, I get a nice error message, 1 was not less than 0. If I say x is, what did I say here, greater than 0, which is true, and x does not equal 1, then you still get a pretty nice error message if you get your parentheses right. 1 was greater than 0, but 1 equal to 1. So I can reason about that. But as soon as you have a third piece in here, like an or, x is greater than 10, which is also false, then what I get is 1 was greater than 0, but 1 equals 1, and 1 was not greater than 10. And what is kind of lost is like what happened first, because really there's parentheses around this one because of the precedence. But I don't get that in my error message, so that doesn't scale that well. If I get any bigger than 3 pieces, then the error message is not obvious. You have to like compare the message to the original thing. So there's something in ScalaTest called diagrammed assertions, which came from, was inspired by Spock, which instead of trying to make English out of it, it draws a little diagram. So this, it just points to each thing and says, well, x greater than 0 was true, but I have an and here with x does not equal 1, which is false, so that means that's false, and then I go an or, this thing was false, so therefore the whole thing. So you can actually kind of figure that out. But that only scales until you hit sort of the edge here, because I'm pointing to the things vertically, right? So if I say x greater than 10, as soon as we go to 2 lines in diagrammed assertions, it falls back to the English, because you couldn't really draw this diagram and point to things on multiple lines. It just is not reasonable. So even this has a scalability problem. So what happens is if the error message in expectations, I'm going to go back to this guy and make it an expect. Oh, not that. Let's do it with matchers. So I'll say x will be greater than 0, and x will not equal 1, or what's the other piece? X is greater. X will be greater than 10. What you get is kind of a combo of the diagrams and the English. So at each node, there's an English error message, but then you can kind of see how the structure is in the logic statement. So I could look at, yes, 1 was greater than 0, but then that was ANDed with a no, so that's why this whole thing was a no. So I can see, this guy, if I can find my mouse, is a no. That makes sense. But then I ORed it with this other thing that turned out to be a no, therefore the whole thing was a no. And this should scale up very large, right? So I think it addresses that issue. And that is what's coming. So what essentially the insight was simply that you can, kind of have one statement of logic that describes a test, that's what a test is. And it is a specification of behavior in code that goes along with the specification in human language that's the test name, right, if you use a for all. So that's what a test is. And then instead of trying to do what Tony Hoare wanted to do, that was his goal, is we are proving the correctness of software. What we're doing is more like science. We're trying it and observing. We're just performing experiments. Our hypothesis is that the code behaves as we expect. That's what we think is going to be true. But we try it. We don't just believe it on without looking at the facts. We actually try it, and then what you're going to get is an observation that's going to either confirm or show you. It'll either, basically, it doesn't prove that it's true. It just, the only thing you can prove, essentially, is that it's not true. So just like science, you can't really prove a theory true, an experiment. But what an experiment can do is say, actually, no, here's one where it doesn't work, right? So I think it's kind of interesting because what predicate logic is usually mapped to in English is like an assertion like x is greater than 10. So it's just an assertion, and then you say, well, that's this formula, and then you simmer it down and you prove something. What this is using logic for is for expressing expectations and observations. So when I say for all x, integers x greater than 0 implies x plus 1 will be greater than 0. That statement of logic can be mapped to this expectation in English: for all x, if x is greater than 0, then x plus 1 will be greater than 0, which is different than saying that it's true. It's saying I'm kind of expecting that's going to be true. And then when we actually execute this code, there is a case where it won't work, which is if x is maxint, you add 1 to it, it's going to loop back and be minint, right? So the observation is int.max value was greater than 0, but int.min value was not greater than 0. So that also kind of maps to the logic statement. So anyway, that's what I wanted to talk about. And before I go to Q&A, I just wanted to mention that what I've been doing at Artima lately is growing it as a consulting company. So we do hire programmers. If you're interested, you come talk to me or email that email address. And also, I'm the community, one of the community reps on the Scala Center Advisory Board. So if you have a concern or a wish or desire for Scala in general, please come talk to me or email me. And that's my question. Does anybody have any question? We have like 4 minutes, I think, a few minutes. Yes?
Hi, is this thing on? Yeah, it is, cool. I can't find it now, but I remember reading somebody's blog post where they were basically taking a look back and comparing TDD with design by contract, which kind of came first. And there were a couple of advantages of the contract approach in that because that was associated with the production code, it would associate not only with the object hierarchy, so you could have tests or assertions associated with the superclass or with the interface rather than with the implementation,
yes,
and then we use them.
Yep.
But also that means whatever is actually running the code could be a property-based test, could be anything else, could be a user. You'd still be able to exercise those.
Yes.
Is that something that you've looked into or something that's being thought about in Scala at the moment?
It's not being thought about in Scala, just because people don't tend to seem to want that. I mean, what was put into Scala was just a very poor man's, if you want to do it, you can do it ensuring and assume. Those can be turned off, but there's nothing to do with like generalizing or making things more specific with subtype, supertype like there is in Eiffel.
Okay, thank you.
So, yes?
So I was a little bit curious. I noticed that, you showed us that assert returns succeeded value.
Yes.
Why not simply have it return unit?
The reason I didn't have it return unit was so that we could have a type at the end of the test, because anything can be converted into unit in Scala. That's value discarding, unless you set a flag in the compiler. So in async tests in ScalaTest, I just felt like future any or future unit was very error prone. So I want it to be future assertion. Well, what's that? And what an assertion is a thing that either returns a singleton or throws an exception. So I thought we needed a singleton other than unit so that you get more type checking. So in this new version of ScalaTest, there's a style trait, set of cell traits that result type of the test has to be assertion. So you get more type checking that way. This one, yes.
In your examples, assume and require seemed to just be synonyms, so I'm not clear on why both of those words exist in this.
Yeah, assume is different in that, let's see, I think X is 1, it throws assertion error, and require throws illegal argument exception. So assume was the Eiffel way, require was the Java way. Assume can be turned off at runtime, require cannot.
Okay.
And that's why assume was there originally, and require was added actually when we were writing the book. But they're both used for both can be used for precondition checks. If you want to do things the design by contract way, sort of the Eiffel way, then assume might be more appropriate. But most people use require. And in fact, in the book, we just put it as sort of there's a footnote that says assume exists in very small print. So anyway, I think, is that time? I think it's time. Anyway, thank you very much.